Hello students, we'll continue our discussion with practical implementation issues with pipelining. A quick recap of where we are. We started addressing all the assumptions that we have made, and we looked at the pipeline buffers that we need to keep, the unfinished instructions. Then we looked at the design choice, design point of whether we can divide the stages into 5 equal parts or not. Moving on, then we started looking at hazards. The very first one was structural hazard, and following that we looked at the data hazards. We looked at some couple of techniques at the hardware and couple of them at the software aspect. And over the past two lectures, we started looking at the branch prediction for handling control hazards. And before that, we looked at some basic techniques like flushing and moving some of the branch resolution logic from the execute stage to the decode stage. In this lecture, we are going to look at what we can do from the software to handle the control hazards. And we definitely see that the control circuitry for the pipeline is quite complex, not as simple as the non-pipeline version. Now let's try to answer the question, can we take the help of compiler to answer the or address the control hazards, right? So what we have is a very intuitive concept called branch delay slot, right? And the technique employed to use the branch delay slot is called delayed branching. Let's look at it a little more closely. So let's say we have a branch instruction I1. Following that, we have the next sequential instruction, which can be called as sequential successor. If the branch was supposed to be taken, then probably we will have the target as, let's say, I10 here, right? If the branch target is somewhere above, maybe of course I started with I1, so I cannot go to the negative numbers, but it can be somewhere before, right? But it still has the sequential successor, whether it is a forward branch or backward branch, right? So the position which is right after this branch instruction, that is the sequential successor, is called branch delay slot. Okay, now let's try to understand why it's called so. One key thing to observe is it will get fetched most of the time. So keep aside the branch prediction part. If we don't have the branch prediction, then what the hardware does by default is to fetch the next instruction, right? Now if the branch was taken, then this fetch instruction in this as the sequential successor or the sequential successor will get discarded, right? And for the jumps which will always go to the target address, this sequential successor will get discarded no matter what, right? So the question we have is, can we make use of this slot? Because it is always getting fetched, instead of discarding it, can we still continue its execution, right? So that is the concept of delayed branching. What it says is, even though the branch instruction, let's say here I1, is jumping to the target, let's say I10, right? If in the previous simple technique to handle control hazards, we were flushing the pipeline, right? And if we look at the execution after I1, we expect I10 to be executed. And if we have fetched, let's say I2, I3, etc., they get flushed out of the pipeline, and we start fetching from I10. What delayed branching says is, I will not discard I2 and I'll continue its execution, and after I2 is fetched, and as it moves to the decode and execute, eventually I10 will be picked and it will be executed. So instead of the instruction execution being I1, I10, I11, etc., it will be I1, I2, I10, I11, I12, so on, right? So that because the branching happens one instruction later than it actually is happening or is expected to happen, this technique is called delayed branching. So let's say we have an ith instruction which is some branch, and if it is not taken, then obviously I plus 1 would be the successor, or in this case this is a delay slot also, and we'll continue execution with I plus 2, I plus 3, so on and so forth. But if the branch is taken, what happens is we typically flush it and we start fetching from I n plus 1, sorry, I plus n. Here is it's the target, and we continue execution from there, right? Branch delayed branching says, instead of flushing, either the branch is taken or not taken, I will place some instruction there which would be either the successor or some other safe instruction. Okay, here in the second example I put it as I plus y, so maybe it's some safe instruction that we want to execute, right? So this concept of delayed branching is effective as long as the compiler is able to find such safe instructions. Now, why do I call it safe instruction? The reason being, we are placing a new instruction there, right? And if you remember the basics that we discussed on how we can understand control dependence, it clearly says that we should not change the sequence such that a new instruction gets under the influence of branch, or an instruction which is already under the influence of branch will come out of its influence, right? So the compiler now needs to carefully pick such an instruction which would be executed no matter what, right? Let's say if you have the code if and else, right, and after else part you have some fall through code. Now let's say we pick some instruction from this fall through code and place it right after the if statement. Now you can the immediate question that would have is, let's say I'm trying to do something with some variable, let's say x10, and I'm using that in the fall through code. So obviously that is not a safe instruction because the data hazard, oh sorry, the data dependency is violated. So that is the reason the controller needs to carefully choose. It can have three possible scenarios. Let's say we have instruction I, add x1, x2, x3. After that we have a BAQ, x2, x0 and label. Let's say the target instruction is somewhere below, and the instruction which is right after I plus 1 is the delay slot according to the definition. This code can be transformed by the compiler to something like this. So the add instruction has been moved after the BEQ instruction. And to do this, the compiler needs to make sure that the variables, there is no dependency, data dependency between I and I plus 1, first thing. The second one is the value of x1 which is not being changed, whether it is taken or not taken. Obviously it is not changing, right? So even if we had taken the branch, maybe somewhere within the BEQ and the label, let's say we are using x1, so that value is again given by ith instruction. So even after I move it to the delay slot, it will still be same. And let's say if the value of x1 is being used somewhere after the label, means the target of this branch, right, the same thing would happen because the add instruction here gets executed even if the branch is taken. So either if the BEQ condition x2 equals to 0 satisfies or not satisfies, the add instruction gets executed and the value of x1, the correct value of x1, will be used by both taken or not taken paths. The second scenario the compiler can possibly have is something like this. Let's say we have an instruction I plus 1, add x1, x2, x3. Then we have a branch instruction right after that, BEQ x1, x0 label, and let's say it's a backward branch, right? It's jumping to some instruction label with with label here subtract x4, x5, x6. Now we cannot use the scenario A here because there is a dependency, data dependency between I plus 1 and I plus 2. So the compiler cannot move I plus 1, sorry, this add instruction below this BEQ, right, which is the delay slot. What it can possibly transform is something like this. So we have the I plus 1 instruction here, I plus 2 instruction here. In the branch delay slot, it can place the subtract instruction by changing to the target to the instruction below it and placing this instruction in the delay slot. Now, if you think about it, how it would work, it would most likely work when the branch is taken, means the backward branch is taken most of the time, right? In that case, what typically happens, let's say we are iterating through n times, or let's say 10 times. The very first time the value of x4 is calculated and we start executing, and when x2 is executed, we go back to the same instruction when in the second iteration, and again we calculate a new value of x4, so on and so forth, right? So the same thing would happen here also. The very first time the subtract instruction gets executed, and then we execute the loop, and when we are executing I plus 2, we right, and we find that this branch will go back, then the subtract instruction which is in the delay slot also gets executed, and its new value, new x4 value, will be used by the next iteration. So the compiler can do such a reorder in the instructions if it somehow knows that this branch will be taken most of the times, right? So this, which is typical for loops. The other possible scenario is where we have a forward branch, right? We have an add instruction, and following that we have the branch instruction. They have a data dependency, so it will not belong to case 1, case A, and it will not belong to case B also, because it's a forward branch, and the target is a label here, right? And we have delay slot. What can the compiler do in such scenarios, right? Let's say if it finds some instruction I plus 5 or x which is or x7, x8 and x9, maybe that can be placed in the delay slot, right, as the instruction right next after the BEQ. Now when will this work? If we know that even if the branch is taken, the value of x7 is not being used. Only in such scenarios the compiler can take a call that this is a safe instruction. The same thing here. Once we change this and let's say the branch was not taken, we are calculating x4 unnecessarily. So the compiler needs to make sure that the changed x4 value is restored, or it needs to pick the instruction such that this x4 is not used at all. Okay, so these are the three possible scenarios, and the compiler needs to analyze the data dependencies, the control dependencies, and only then it can take a call on whether it can fill the delay slot or not. Okay, so delayed branching, in delayed branching method of handling control hazards, the compiler is the sole player and it has a lot of work to do, right? It needs to find a safe and useful instruction to fill the delay slot. If we place some dummy instruction, or some useless instruction, then anyways we are losing performance because it's useless, right? So it needs to deeply analyze the sequence of instructions and the data flow and the control flow during the compilation itself, right? Now, what happens if we have more than more delay slots? What we have seen prior is just one delay slot, right? But in deeper pipelines where we have 14 to 20 or maybe even more stages, the branch delay slots might be more than one. So what needs to be done? the compiler needs to uh, provide so many safe and useful instructions, right? So it is a huge task and it might not be uh, possible all the time. That is the reason delayed branching has very limited scope. And uh, primarily because the compiler has a limited scope of finding the safe instructions. Now, if we look at the hardware to support delayed branching, what needs to happen is instead of flushing the pipeline, we should continue with uh, the next instruction. Let's say we have moved the logic from the execute stage to decode stage and we have only one possible bubble. Now instead of flushing that, we should continue with that instruction, that is the instruction in the delay slot. We should at the hardware we expect that the compiler has done its job and placed a save instruction. We continue executing that, and then the very next instruction after that will be a fall through instruction, meaning the sequential instruction or the target instruction from the taken path, right? So that is the understanding between the compiler and the hardware. So apart from the checking the control and data dependencies, we also saw that in two of the scenarios the compiler needs to have some knowledge on whether the branch will be taken most of the time or whether it will not be taken most of the time, etc. Right? In scenario B, we are the compiler um, the change made by the compiler is useful if the branch is taken most of the time. In the scenario C, uh, the change made by the compiler is useful when the branch will not be taken most of the time, and we continue with the sequential next sequential instruction, right? So this delayed branching as a concept is very like I said, it's very intuitive because the hardware will always fetch the next instruction and instead of flushing we can use that, but it has very limited scope. It was used heavily in the earlier risk processors, but once the branch prediction concept has been explored more and more, and now we have predictors which have accuracy as high as 98 99%, the delayed branching has been put aside. So the delayed branching concept has been explained in 822, 823, and 824 pages of the Computer Architecture, a Quantitative Approach book. Please go through that, and if you have any questions, we can discuss during the live session. With that, I'll pause this short lecture. Thank you.